Good afternoon. I am Mr. Ish. Thank you for joining me for this video. Calculus concepts that are frequently tested. If and when you do take that calculus semester class, the first one, normally it could be a semester or 2 semesters based on your institution, but when you do that first exam, you could very likely see either or both of these questions as I did 20 years ago in my class. These are two favorite questions which professors really like to test students on. Look here at question A. Demonstrate the opposite nature of the derivative and integral procedures. Related to the fundamental theorem of calculus, opposite sides of the same coin, derivatives and integrals. Question number B. Prove the derivative scheme for f of x equals e to the x. Why specifically this function? They like to test this because it's non-linear, and it's an interesting function in the sense that if you look at this function, you do its derivative, and the same function you do its integral, the antiderivative and the derivative, they're the same. Anyhow, that's just an interesting fact, but you are very likely to see a question similar to this, if not these, on a semester exam. So we will delve in both of these questions in a thorough but simplified manner in this video, so stay tuned. One by one, let's look at both of these questions. The first question was you had to show that the derivative and the integral are opposites of one another. We know that by the fundamental theorem of calculus, we have to show that, and the showing part is your question. If we designate this function right here as a function we want to utilize, because you don't want to use anything specific, you want to use a generality. That's like saying y is equal to x to the power of n. Use the properties of natural logs and get rid of that exponent. ln y is equal to n ln x. See? We've invoked the natural logs and gotten rid of the exponent. Do implicit differentiation. We know how to do that. D over dy ln y, and then dy over dx is equal to n derivative of ln x. Why is the derivative not applying here? Because it's a coefficient or a constant, you can just push it outside. You're solving for dy over dx. Derivative of ln y is 1 over y. Derivative of ln x is 1 over x. Solve actually for dy over dx in this last step. Dy over dx is equal to n over x. Y comes on the other side, cross multiplies. You have ny over x. But what was y? Y was equal to x to the n. Resubstitute that. Y prime or dy over dx, these are all synonymous terms. Y prime is equal to n x to the n over x. But this n x to the n over x can be written in a better way using the laws or the properties of exponents. You can do n x to the n minus 1, because this thing can come up. When you're dividing expressions where the bases are the same, the exponents subtract, and this is what we have. So we now know that the derivative of anything which is f of x is equal to that. So we can write f prime is equal to this right here. This is an indirect way of proving the derivative power rule template. Remember the power rule? This is how we can prove it. Anyhow, f of x was this. Derivative of f of x is this. Now you take the integral of this right here, which happens to be your derivative, which happens to be the function which is feeding into this integral procedure, and you integrate this. Bring the n outside. We know that when we're doing an integration procedure, the constant or the coefficient can be pushed outside, and I've shown you a video why it has no effect on the outcome. It's either the same whether you did or you did not. You're looking at x n minus 1 dx. The template for anything like this, a polynomial, is always, as you know, n plus 1 over n plus 1. We know that for polynomial integral. So do that over here. You have n x to the n minus 1 plus 1. Here's my plus 1 coming into place. And here the same exponent plus 1. From this step right here, we have nx n minus 1 plus 1 over n minus 1 plus 1. These minus 1 plus 1 will cancel out. What will we be left with? Let's put it right over here. We have n x to the n, right? See this n retained, this n, over n. These n's cancel out, you get left with x to the n, which is what? This right here represents your antiderivative, capital F of x. And look what we started with right here. Here and right over here. So what have we shown you? We started with the function f of x, which was equal to x to the n. We determined a derivative which was equal to n x to the n minus 1, which I've shown you. Then we did the integral of that to arrive at an antiderivative. The antiderivative was x to the n, which is the same as your original function. And this statement right over here shows you the opposite effect of the derivative and the integral. You start with 1 and you undo it with the other. What is that undoing? When you started with 1, you ended up with the derivative. You undid that derivative by taking that derivative and integrating it and ending back to your original function, which is the same as your antiderivative, and that right there is this question done. The second question for this right here video, very likely you can see this in your exam or your paper, final paper, which you know will always be problems, not really multiple choice. In a calculus exam, it's very unlikely you'll see multiple choice questions. You'll have to actually solve them out, and they'll have you solve out more conceptual type of questions versus the straightforward questions. F of x is equal to e to the x. We have to show and demonstrate the template for this in terms of the derivative. If you were to graph it right here, let's just graph it, e to the x. That's my function, and you know it's always 0, 1, but that's besides the point. We could have had a coefficient here anyhow. If you pick a specific point on this graph, and we'll call that x right over here, in terms of this coordinate pair, that coordinate pair, and I'm going to write it over here, is x comma e to the x. If you go h units away, right, plus h units away, and you come right here on your graph, this coordinate point here will be x plus h comma e into x plus h, right? You see that, right? x1, y1, x2, y2. If you did a slope determination over here, you'll do y2 minus y1 divided by x2 minus x1. We'll have e to the x plus h minus e to the x. See, y2 minus y1 divided by x2 minus x1, x plus h minus x. When you simplify this out, what are you really getting? You're getting e to the x plus h minus e to the x over h. Okay, that's your slope which is coming out. But you know the slope of a secant line is not the same as a derivative. The slope of a secant line is quite different than a derivative because you're looking at the average rate of change. To convert the slope of a secant line into a derivative which is representative of an instantaneous rate of change, you have to apply a limit. Remember, to answer this question, to show the derivative, there are many ways of doing it. I'm showing you only one way, and on your exam you'd only have to show one way. You would have to apply this limit to this template here or this formula here, and then you would be looking at a tangent line. So let's apply limit as h approaches 0. We have e to the x plus h minus e to the x over h. To complete this question, we ideally need room, and let's create some of that room. We're gonna erase this because everything I've shown you up till now has led me to that, and we can very well erase it. There's nothing wrong with doing that. Let's look at this step over here, this specific part right here. Let's just say here a to the x plus y in terms of properties of laws of exponents is the same thing as saying ax, ay. Think about it. When you have two expressions which are multiplying and they have the same base, the exponents add. This right here is equal to that. How can I demonstrate that? And let's show you. Limit as h approaches 0. I'm looking at e to the x times e to the h, then the rest of the expression over h. Think about it. Same basis, if I combine them, I'm adding the exponents, so I've rewritten this as this. Why did I do this? Because of this specific reason why I can now isolate e to the x, and I can bring out e to the h minus 1 over h. Use the properties of limits where the limit of a product is equal to the individual limits of the substituents that are being applied in that product. What does that mean? I can do a limit as h approaches 0, e to the x times a new limit, because I had these two items multiplying this with this. I can apply individual limits to both of these items, and I can essentially separate them out. When you do the limit as h approaches 0, e to the x, this will always equal e to the x, because there's no h factor here being applied, so this limit is useless. But there's something which needs to be done over here, and we have to do that to complete this. If you were to literally apply 0 in places of these h, what will you get? You'll have e to the 0 minus 1 over 0, you'll have 1 minus 1 over 0, you'll have 0 over 0. You have an indeterminate limit form come in, and since you have this indeterminate limit form, 0 over 0, you can use L'Hopital's rule. When you use a L'Hopital's rule procedure, you can do derivative application in the numerator, and you can do a derivative application in the denominator. But here our variable is not an x, here the variable is an h. If you did a derivative of e to the h, you should just get e to the h. If you did a derivative of 1, you'll get a 0. Derivative of h is just a 1, and you apply 0, you get e to the h. But how can we get from here to here when we're actually trying to prove a template for this type of an expression? We can do so by looking at this other expression right here. If y is equal to e to the x ln y is equal to x ln e. This is just a 1. You do implicit differentiation of this expression right here. You'll have d over dy ln y dy over dx is equal to the derivative of x, which is just a 1. Derivative of ln y is 1 over y, and you're solving for this y prime, which is dy over dx is equal to 1. Y prime, which is dy over dx is equal to y. You take the 1 over y on the other side, it cross multiplies. What was y prime equal to here? It's equal to y. But what was y equal to? It was equal to e to the x. So here I've shown you that the derivative, using a different procedure, using the properties of logs and natural logs, that the derivative of anything which is e to the x will always be e to the x. Hence, using that as an assumption, we can show this to be the case when you're actually trying to prove this scheme. All of this right here boils down to what? Limit h approaches 0, e to the h, right? All of this expression using the L'Hopital's procedure in the numerator and denominator gave me an e to the h. Now we're finishing this up. When you plug 0 into place of h, you have e to the power of 0. All of this comes down as a 1. You have e to the x times 1, and therefore your answer is e to the x. So now you've shown that anything which is f of x is equal to e to the x, you do the derivative of it, right? Derivative, you'll get e to the x, and that's what the question was showing you. And we've done that, and the question has been solved. So keep in mind all the factors that played into this application here. We had a graph over here from which we deciphered and determined the basic definition of a derivative, but for the function e to the x. We carry this limit expression through, separating it into the individual products of this limit, as you see over here. We have an indeterminate limit form which comes into play, for which you have to use the L'Hopital's procedure, but that requires you to do a derivative of something which looks like e to the x when you're trying to actually prove that. But you can go to this alternate procedure or technique to show that anything which is e to the h or e to the x is always equal to e to the x or e to the h in terms of its derivation, and we utilize that, bring that into play, take this to the end to our final derivative, and it's done. So the two questions have been solved out for you. They're conceptual questions. They're slightly tricky, if not so difficult, but this is what you could expect to see on a final exam for your semester calculus test or your semester calculus exam. And this is what you would be expected to produce in terms of your knowledge. Stay tuned. Thank you for watching. Have a nice day.